to our colloquium. Today we have Joel Kamnitzer from Toronto. I think I have to say a few words. So Joel did his PhD from Berkeley in 2005, and he has been in Toronto since 2008. His thesis was about MV cycles and geometric Satake. So today he's going to talk about the generalized affine Grassmannian slices and categorification. So Joel, just take it away.
Okay, thanks, Sachin, for the introduction and the invitation and the nice welcoming with all the Canadian gear. Okay, so indeed, I'll talk about categorification and generalized affine Grassmannian slices. So this is joint work with Peter Tingley, Ben Webster, Alex Weeks, and Oded Jacobi. Okay, so let me begin by discussing the idea of categorification, which is the background for our work. Okay, so I begin with a semi-simple group over the complex numbers. So as the simplest example we can, or not the simplest, but as a main example that we think of as the group of n by n complex numbers with determinant 1. So we call that SLN, special linear group. So we're interested in representations of this group, so actions of this group on a complex vector space. So the main theorem tells us that there are these irreducible representations, V lambda, and they're labeled by a certain set called dominant weights. Okay, so those are the irreducible representations. And these irreducible representations have a decomposition under the, well, any representation, but particularly these, have a decomposition under the maximal torus of G. So every group, semi-simple group, has a maximal torus. For example, when G is equal to SLN, this torus is simply the diagonal matrices. And we can decompose our representation under the action, and we get a decomposition into eigenspaces for this torus. So here's just a quick example. Maybe we take our group to be SL2, so it's a subcase of SLN. In this case, this dominant weights is just the natural numbers. And for any natural number, n, there's an irreducible representation, Vn, so it's like this V lambda I said before. And what is it? Well, in this case, it's quite simple. It's just the n-fold symmetric power of C2. Another way of thinking about that is degree n polynomials in two variables, x and y. And our group SL2 acts because it acts on this C2. Or if you like, it permutes these variables, x and y. Another way of thinking about the action is that this vector space is a basis, x to the n, well, let's start this side, y to the n, x, y to the n minus 1, x squared, y to the n minus 2, and so on up to x to the n. So that's our basis. And our group, well, in fact, our Lie algebra contains certain elements called E and F. You know what they are if you went to my pre-talk. And they act on this representation by the differential operators x d by dy and y d by dx. So they move between these basis vectors. Well, there's some coefficients you pick up along the way as well. Okay, so that's an example of one of these representations. And this pattern, well, this example is somehow, the generalization of this example is that I mentioned that there are these weight spaces for our representation. So these are the eigenspaces for the action of that maximal torus, those diagonal matrices. And we can move between these eigenspaces using certain elements of our Lie algebra called EIs and FIs. So our Lie algebra of our group contains special elements called EI and FI, which move us between these weight spaces. And how do they move us, or where do they move us? Well, there are these things called simple roots, which are how you move around. So here's an example. So here's an example where G is equal to SL3 now, so not SL2. And we have the dominant weights of SL3 are the integer points inside a certain cone. The cone is what's drawn here in blue. So the integer points in this blue cone are precisely the dominant weights. And for our given lambda, so we're working with this, that lambda there, that's our lambda. And the rest of the dots are the mu's where this V lambda mu is non-zero. And in fact, it's one-dimensional where there's only just a dot. And at these places here, the V lambda mu is two-dimensional. And this F1 and F2, those are the directions in which we move when we apply F1, F2. So if we can move from this weight space to this weight space, then we can move to this one with F2 and so on. So we move around between our weight spaces using these EIs and FIs. So that's a picture of a representation of our group G. So we have a bunch of weight spaces and ways moving between them using these elements of our Lie algebra. Okay, so this is a very classical, well-understood story. And then about 20 years ago, Kovanov proposed the idea of categorifying these representations. So what was Kovanov's idea? He said, well, here we have vector spaces, these weight spaces. Let's replace them all with categories. Okay, and let's replace these linear operators between them with functors. And what property should we have? Well, we should recover our old setup by taking the Grothendieck group. So these categories should be some kind of abelian category or triangulated category. So we can take their Grothendieck group and recover a vector space. And this Grothendieck group should just be the old vector spaces we had before. So you might ask, why did Kovanov think we should try to categorify them? Well, one reason was because in simple examples, it was, for example, for those n-fold, for those representations of SL2 I mentioned earlier, it was clear how to categorify them. And so it seemed like a natural thing to try to categorify them in general. And one good thing about categorifying them from Kovanov's perspective is that it would lead to some interesting knot invariance, so I won't talk about that part of the story today. Okay, so but this is the main problem that Kovanov proposed in 2000. So this problem was many people worked on it, and it was solved in some sense in a very algebraic way. So effectively by Kovanov and Lauda, and sort of independently Rouquier and other people too. There's many other people who worked on this approach. So it's an algebraic approach. So what did they do? They introduced some certain algebras which are now usually called KLR algebras, or Kovanov, Lauda, and Rouquier. These are diagrammatic algebras. So diagrammatic algebra just means an algebra where we think of the elements of the algebra as being diagrams, or sometimes linear combinations of diagrams. So here's a diagram. I mean, what kind of diagrams? Well, in this case, they're diagrams which look sort of roughly like that. So some kind of like strings with dots on them. And so this is not algebra, which is denoted like this, whose elements look like these strings with dots. And from the very definition of its algebra, it was possible to build functors like this between their category of modules. So we go from modules for one algebra to modules for another algebra. And so we have an algebra for every one of these. Here we had different weight spaces, and I wanted to replace these guys with categories. And the way I do it, I replace them all with algebras, and then I take the category of modules. So think of, in this diagram here, think of to each point in this diagram, I attach an algebra, and then I take modules over that algebra. Okay. And so people were able to use this to build functors between these categories, and this categorified the representation of V lambda. So this was very nice, but some people well, I don't know. No, many people liked it. But now I want to talk about a more geometric approach to categorification. So like you might ask, where does these algebras really come from? Why do we have these weird algebras around? Funny looking defined with funny looking diagrams. Okay, so so now we're going to switch gears like completely and talk about affine Grassmannian slices, and then eventually we are going to come back and combine things together. Okay, so one interesting way of studying representations of our semi-simple group is using something called the geometric Satake correspondence. So it's quite a long mouthful and it sounds complicated, but it's not too complicated. So what do? First, we invent a new group called the Langlands dual group. Well, it has the word Langland, so again, it sounds complicated, but actually usually this G check is almost the same as G. For example, if G is SLN, then G check is just PGLN. So GLN mod the diagonal matrices. And then, so for the first approximation, you can just imagine that G check is the same as G. Then using G check, we build a very interesting space called the affine Grassmannian. So it's defined as you take your group G check and take its points over Laurent series, and then divide out by the points over power series. So explicitly, you could think of this G check as SLN. You'd be taking n by n matrices where the coefficients are these Laurent series, and then quotienting by the subgroup of n by n matrices where the coefficients are power series, maybe n by n determinant one matrices. And how to think about this space? Well, if you're familiar with ordinary Grassmannians or flag varieties, this is a kind of infinite dimensional version of a Grassmannian or a flag variety. Okay, what are the key features of this space? So the first feature is that it comes with a distance map. So there's a map measures distance between points in this affine Grassmannian, but it's a funny kind of distance. It's a kind of discrete value distance. So it takes values in this cone. So for example, this could be the positive integers or some integer points in some cone. So that's in distance. And then using this distance, we can, this affine Grassmannian has a base point 1, which just comes from the element 1 inside here. And we take those points where the distance is like less than or equal to lambda, and that defines us a thing we call a lambda bar. If we don't put the bar, then we have equality. So this is a finite dimensional projective variety. Another way of thinking about this lambda is it's the same as the orbit of this G check of power series on a point T lambda. So what are these points T lambda? Well, the way this Langlands dual group is set up is that the co-weights of this Langlands dual group, so Hom from C star into the maximal torus of G check is X, which was the weights of our original group. So given any weight of mu of our original group, we get a point T mu in this affine Grassmannian, which you can think of as being, in our matrix setup, you can think of as being a diagonal matrix whose entries are powers of T. Here's a pretty example. We take G check to G to be SL2 and G check to be PGL2. In this case, imagine we have a tree. Here it's a picture of such a tree. I know it's very small, but that's because when I copy the image in here, it is not very high resolution. So if it blew it up anymore, it doesn't look good. Okay, so here's a tree. It's an infinite tree, and at every node, there's many things coming out. Well, in this picture, there's just 3 things coming out, but I want to consider P1, like CP1. So infinitely many things labeled by a projective line coming out of each node. So imagine at each node, we have P1 entries coming out. And the affine Grassmannian is the set of vertices of this infinite tree. Okay, and this D is just the usual metric in the tree. So for example, and here's our base point. So for example, if we were to study the things of distance 1 from this base point, well, we pick up just this whole P1 around the base point. The red thing isn't working very well right now. Okay, we had to pick up the whole...
Can I ask you a question?
Yeah.
So this branching, is it the branch points are dense, or is it like you're picturing they're discrete?
Well, this picture would be the case where we're working over the field with 2 elements.
Yeah.
So the set of branches from a given point is parameterized by P1. So
yeah, no, but I'm just asking about the branch points itself. It's like, because this looks like a Berkovich P1, so that has infinitely many branching points, and they're, here they look like they're separated. So these segments that you write, there's one branch at the center, then there's another one. Are there also branch points in these segments that you
No.
drew? No. Okay. Thank you.
And so if we were to look at the points of distance 1 from this guy labeled a plus in the middle, we get P1. If we look at the points of distance like and most 2 from the middle here, we get all these guys which are distance exactly 2, plus we get himself back because he's also of distance, well, he's of distance 0, which is less than or equal to 2.
Right.
So some of these, the topology, the way the geometry works out, some of these points here, they're kind of quite close to back to where you started.
I see.
Okay. And in general, there's a kind of picture like this of the affine Grassmannian called a affine building for any group G. Only in this SL2 case does it actually look like a tree. Hey, My thing is frozen. Ah.
Maybe
Hello,
you can
iPad.
disconnect and
What's
then-
wrong with you? Try that again.
Huh, now it's upside down.
But it's also slow. What's wrong?
All right.
Seems to have like come back to life. Hopefully that we don't get that again. Okay, great. Here we are.
All
Okay.
right.
So here's where we were. We had this affine Grassmannian. We have these lambdas or lambda bars. So they're like, you can think of a kind of sphere around the origin, the points of this distance lambda. Okay. And they're finite dimensional. Well, once we take the bar, we get a finite dimensional projective variety. The affine Grassmannian itself is infinite dimensional, but this thing is a finite dimensional projective variety. For example, I said a P1 in that special case. Okay, now we can define a kind of complementary subvarieties of the affine Grassmannian, which are called, which are these slices. They're infinite dimensional, in fact, finite codimensional in the affine Grassmannian, and they're defined by taking the orbits of this complementary group G1 T inverse. So I have this GT inverse. It has an evaluation map to G, so G check T inverse is an evaluation map to G check, and I take the kernel of it, and it's called this first congruent subgroup, and I take the orbits of this thing. So the detail is not that important if you're thinking about the analogy with Phi varieties. These are like Schubert cells, and these are kind of like opposite Schubert cells. Except in this case, the opposite Schubert cells turn out to be kind of infinite dimensional. And then I intersect these pairs of a Gur lambda bar and a W mu, and it produces what I call W lambda mu, which is affine Grassmannian slice. So there's like a funny picture of it. So here we see the kind of finite dimensionality of the Gur lambda bar and the infinite dimensionality of the W mu, and then this is sort of place they intersect. Okay, again, it's analogous to taking Schubert, maybe to be more precise, analogous to taking sort of Schubert variety and intersecting with opposite Schubert cell. That would be the analog in the finite dimensional flag variety or Grassmannian situation. So these spaces are the ones we're interested in this talk called affine Grassmannian slice. Okay, okay. So now I want to say a theorem which is part of the geometric Satake correspondence. So it says that first of all, if we take this Gur lambda bar and we take its intersection homology, so intersection homology, that's a homology theory well adapted to singular algebraic varieties like this Gur lambda bar. If we take the intersection homology of Gur lambda bar, then then it's naturally isomorphic to the representation V lambda of the group we started with. Let's take a quick example of that. Imagine we started with the group SLN, and we have the kth fundamental weight. So our V lambda is the representation wedge KCN. That's the irreducible representation of SLN. And the Gur lambda bar, it turns out in this case, is this Grassmannian of all k-dimensional subspaces of Cn. It turns out in this case, Gur lambda is closed and is actually equal to an ordinary Grassmannian. And and also in this case, we would have intersection homology, but since the space is smooth, we can just take ordinary homology or cohomology. And it's well known that the homology of this Grassmannian has a basis indexed by the Schubert varieties, and there's n choose k of those Schubert varieties, which is the same as the dimension. So there we see the equality of at least the dimensions of these two sides. And this geometric Satake correspondence is saying that this isomorphism is a natural isomorphism, and it works for any lambda. Moreover, if we are interested in weight spaces of the representation, we can recover them from the intersection homology of these slices, W lambda mu. Okay, there's actually like slight lie in here. It's not quite the intersection homology, it's more the hyperbolic stocks of the intersection homology, but it's not too important. Okay, so the main message is that we are interested originally in this representation and its weight spaces. Maybe we want to categorify it. Well, at least here we're given, these guys have a nice geometric incarnation using these affine Grassmannian slices. And one thing is this only really works for mu dominant. We'll see what happens when mu is not dominant shortly. Okay, now we're going to talk about quantization of these affine Grassmannian slices. What does quantization mean? Well, it turns out this W lambda mu has a Poisson structure. So Poisson structure, it's like related to the notion of symplectic structure from differential geometry. But in this case, I just mean a purely algebraic thing. I just mean that if we take it's an affine variety, and if we study its coordinate ring, it has a multiplication, but has another kind of multiplication, which is called a Poisson bracket. Okay, so then quantization of this deformation quantization of this affine Grassmannian slice means we look for an algebra, which I'll denote y lambda mu, which is an algebra over polynomials in h bar. And to first order, so when we set h bar equals 0, we recover the original algebra. And this algebra y lambda mu is non-commutative, and its non-commutativity to first order is given by the Poisson bracket in W lambda mu. So W lambda mu controls the 0th order, like what happens when h is 0, and the first order of the non-commutativity coming from the Poisson bracket. And I don't know if this meant, I've snuck a definition and I don't know, theorem or something in one sentence here. So there is a deformation quantization of this space, which is called a truncated shifted Yangian. So there's a natural way to define, in fact, a whole family of these deformation quantizations. So, and these algebras, y lambda mu, they can be defined as subquotients of the Yangian. So they have a very natural description in this setting, which I won't go into, but it can be studied. Let's go, though, a special example, which is going to be quite important later. So imagine we take G to be SLN. Then we can take lambda, well, we have many choices, but for example, we can take the first fundamental weight. And we can take the nth multiple of the first fundamental weight, the same n. And in that case, mu equals 0 is a natural choice. And then the corresponding affine Grassmannian slice is a very natural variety. It's just the variety of all n by n nilpotent matrices. For example, in G is equal to SL2, the variety of all n by n nilpotent matrices is this cone, this quadric cone, C3. But in general, we have all n by n nilpotent matrices. And what's our affine Grassmannian, what's our truncated shifted Yangian in this case? Well, it's closely related to the universal enveloping algebra of SLN. It's in fact, the universal enveloping algebra of SLN modulo the positive part of its center. Or you could model by other central characters too, if you like to get the other quantizations. But the simplest one is like this. Okay, so here we see a very classical looking algebra as our truncated shifted Yangian. So my whole message is that don't be scared of these truncated shifted Yangians. They're just nice things like SLN, universal algebra of SLN. And maybe surprisingly, we'll see soon that thinking about SLN as a truncated shifted Yangian actually allows us to solve a previously open problem concerning the Lie algebra SLN. But let's go back to our main goal. So remember, our goal was to categorify V lambda. That means we wanted to have one category for every weight space of our representation.
Can I interrupt you for just a sec?
Yeah, go ahead, Dave.
What is the representation there? Is that the symmetric power for the example that you just did?
Yeah, it's sim n of Cn. Like the n. Yeah.
And so we get the 0 weight space of that somehow.
Yeah.
Cool, thanks.
Which is only one-dimensional, but as we'll see later, somehow it's not very different than thinking about categorifying this representation, the non-irreducible representation like this. And this weight space is n factorial dimensional.
I also had a question about how this slice, so I guess because your slice lives in the affine Grassmannian, which is, you have matrices with t's in them, and the nilpotent matrices they don't have any t's, so you just set t to 0 or something like this?
That's a great question. So the map actually is not quite, it's almost that though. The map takes a matrix X. Oops. Yeah, the map from these nilpotent matrices to the affine Grassmannian. I'll try to write very small in here. It takes a matrix X to the matrix identity plus T inverse x. Notice that because the matrix is nilpotent, this guy will be of determinant 1. This characteristic polynomial is just the 1. So this guy will have determinant 1. The characteristic polynomial of x is just 1. Check. Because x is nilpotent, this identity plus t inverse x has determinant 1. And in particular, it's invertible. And it defines a point in the affine Grassmannian. So that's the map.
Makes sense. Thank
Okay.
you.
So let's just remind our goal is, again, to categorify this representation V lambda. That means we wanted to attach a category to every weight space of the representation. And we saw we can attach a space, W lambda mu, to each weight space. And then we can attach an algebra, because it's a quantization of W lambda mu. So, so then it's natural to look at categories of modules over this algebra. So we could try to categorify V lambda using categories of modules for these algebras, Y lambda mu. But there's an interesting problem that this brings up, which is how can we define these space, the space and this algebra in the case when mu is not dominant? In fact, you might ask, well, can't you just take the same definition even when mu is not dominant? You do get a space, but it doesn't have the desired properties. Okay, so so it turns out that W lambda mu, I've defined it using the affine Grassmannian, but it actually arises in a completely different way. And in that way, it's easy to see how it generalizes. So this way is using a theory of something called Coulomb branches. So this is something when we embarked on studying these affine Grassmannian slices, I don't know, 10 years ago, we never heard about these Coulomb branches. I only heard about them 5 years ago, but it turns out they're a great tool to help us. Okay, so let's change gears now. So I take another group, H, which is going to be some kind of reductive group. In fact, this group H will for us always be a product of general linear groups. So in fact, it's going to be a product of general linear groups indexed by the Dinkin diagram of our original group. And V will be a representation of H. And given this data of V and H, physicists can define something called supersymmetric 3D quantum field theory, which I don't know anything about, but they tell us that there's 2 spaces that you can produce from this 3D supersymmetric quantum field theory. One space is called Higgs branch, and the other space is called Coulomb branch. From what I understand, this theory has like a lot of vacuum states, like lowest energy states, and like so many that any point in this Higgs branch or Coulomb branch is like a lowest energy state. Okay, so what's this Higgs branch? Relatively easy to define mathematically. It's the Hamiltonian reduction of the cotangent bundle of V by the action of H, which means you take V plus V dual, that's the cotangent bundle. It has a moment map to the Lie algebra of H. You take the 0 level and divide out by the action of H. And the Coulomb branch was much harder to define. It was defined mathematically in a paper by Braverman, Finkelberg, and Nakajima about 5 years ago. And the definition is roughly like this. You start with the stack quotient V over H. You consider the space of all maps of P1 into this stack quotient. And you take the homology of this space of maps. And this homology has a natural convolution algebra structure. And it actually is a commutative algebra. So this homology is an algebra using convolution in some sense, and you take spec of it, and that's the definition of the Coulomb branch. So that's quite a mouthful. Let's look at a simple example. We could take H to be C star, V to be Cn. In this case, this Higgs branch is the cotangent bundle of projective space, and the Coulomb branch turns out to be the ADE singularity C2 mod Z mod n, which actually this actually arises as an affine Grassmannian slice for any W lambda mu of the form lambda minus alpha I, where n is equal to the pairing between lambda and alpha I or something like this, plus minus 1. Okay, so here we see a simple example of it. Now, this definition looks pretty wild. To really work with it, you need to think about what's about the stack, about this space of maps, which is quite complicated, and then about its homology. So it looks very wild, but it turns out that it's actually kind of useful. So here's a theorem of these guys. So let's take G, lambda, and mu to be as from the beginning of the talk. So what we're now going to find an H and a V. So I won't like exactly tell you what they are, but they come from the Dinkin diagram of G. So what does it mean? It means that we want H to be a product of general linear groups indexed by that Dinkin diagram. And which ranks of those GLNs are controlled by lambda minus mu, turns out. And then there's also a H. So it's going to be a vector space of representations of a quiver, where the quiver is given by this Dinkin diagram. Okay, so what do these V and H come from? One way of thinking about them is that the Higgs branch, which was just this Hamiltonian reduction thing, is a Nakajima quiver variety. So if you've seen the theory of Nakajima quiver varieties before, you know what V and H I'm talking about. And if not, just take for granted that I mean it. H is just some product of GLs indexed by the Dinkin diagram, and V is represents some HOMs between vector spaces related to the Dinkin diagram, and we also have the data of lambda and mu in there. So if we do all that, and we build this Coulomb branch by this complicated definition, it turns out the Coulomb branch is W lambda mu. So when mu is dominant, and this allows us to define W lambda mu and Y lambda mu when mu is not dominant. Now you can go back afterwards and try to, you can figure out what this ends up being, this W lambda mu when mu is not dominant, and you can describe it without using this language of Coulomb branches as a certain space of matrices. And similarly, you can just find this Y lambda mu purely algebraically by kind of generators and relations prescription. But to really know that you had the right answer, it's helpful to know that they actually arise as Coulomb branches. Okay, so this was about 5 years ago. Okay, so now discuss some results that we have using these W lambda mu's and Y lambda mu's. Okay, so inside of our algebra Y lambda mu, there's a big subalgebra called a Gelfand-Cetlin subalgebra, and it generalizes the usual Gelfand-Cetlin subalgebra of the universal developing algebra. What I mean by that, let me just write that. So inside the usual USLN, we have its center. And in fact, we can consider inside here some other SLK embedded as like K by K matrices in the top left corner, and we can consider its center. So the usual Gelfand-Cetlin algebra of this universal developing algebra is the subalgebra made by using all these centers. And it gives us a big maximal commutative subalgebra of this SLN. And inside any Y lambda mu, any of these affine Grassmannian slices, or their quantizations, there is this big Gelfand-Cetlin subalgebra. From the viewpoint of the geometry, we can think of this subalgebra as actually a maximal Poisson commutative subalgebra of the coordinate ring. It gives us a complete integrable system on our variety. And in fact, from the viewpoint of this Coulomb branch, for any Coulomb branch, there's such a big Gelfand-Cetlin subalgebra. It comes, if you unpack this definition, this ends up being some kind of equivariant homology because of this group H here. So it ends up, this big commutative subalgebra ends up coming from the equivariant cohomology of a point. Okay, so very natural subalgebra. Maybe I should say since there's a lot of experts on Yangians in the audience, from the Yangians viewpoint, this Gelfand-Cetlin subalgebra is just the natural sort of Cartan subalgebra of the Yangian coming from all the HIKs, or whatever you want to call them, HIS, all the higher modes of HI. Okay, so we're interested, I mentioned we were going to be interested in a category of modules for Y lambda mu. So we have these algebras, y lambda mu, and we're going to study modules for them. And what modules we're going to study? We're going to study Gelfand-Cetlin modules. So that means category of modules for these algebras on which this Gelfand-Cetlin algebra acts locally finitely. So the module decomposes into a direct sum of generalized eigenspaces for this Gelfand-Cetlin subalgebra. Turns out that's a very natural category of modules to study. And we proved, so these are the people I mentioned at the beginning of the talk, Tingley, Webster, Weeks, and Jacobi, that there's an equivalence of categories between this category of modules and the category of modules for this algebra here. So this is the algebra I mentioned at the beginning of the talk. This is this KLR algebra. So some combinatorially defined algebra defined with some funny diagrams. And we define an equivalence of categories between modules of our algebra and this combinatorially defined diagrammatic algebra. And this equivalence is defined in a very explicit fashion. Like you're given a module, you do this procedure, you get a module for this algebra. Like it's very kind of hands-on. Okay, and okay, so I should mention before moving on, there's like some like lies involved. Let me just mention exactly. So I said that there's actually not just one y lambda mu, but it comes in a family of quantizations. So just like we could take the universally enveloping algebra SLN modulo the zero central character, we could also modify by other central characters and get other quantizations of the coordinate ring of the nilpotent cone. So we actually get a whole family of quantizations here. So there's actually a parameter on the left side, and then it affects, there's actually not just one KLR algebra that we're dealing with, but a whole family of KLR algebras. And because of that, we don't just study the KLR algebras, but these generalizations of KLR algebra studied by Ben Webster. So we call them KLR W algebras. And in fact, those even aren't enough. We have to modify and introduce new kinds of KLR W algebras, which we call metric KLR W algebras. So up to some generalizations, though, this is the basic idea. Gelfand-Cetlin modules here is equivalent to KLR modules here. Okay, so let me explain some good things about this. So the first good thing is that I said we wanted a categorification. Well, here we already knew, I told you from those other people's work, that algebraically we do have a categorification using these guys here. So we have these modules for these KLR modules for these KLR algebras, and we have natural functors between them. In fact, this whole KLR algebra was sort of cooked up so there would be such functors between them. And we can use that and this equivalence to give us functors, I'll call them EIs, between Gelfand-Cetlin modules for y lambda mu and Gelfand-Cetlin modules for y lambda mu plus alpha I. So we do get a categorical action, namely these functors, on these Gelfand-Cetlin modules that we wanted. But now you could say, well, this is kind of cheating. You started the talk by saying that this algebraic category, well, not started, but somewhere in the talk you said this algebraic categorification was not that good and we wanted to see it more geometrically, but now the only way you've gotten the categorification is via the algebra, so it's not so good. And I agree, that's why this big question mark is here. So this is not so good because we'd like a way of understanding these functors purely from the viewpoint of affine Grassmannian slices or truncated shifted Yangians without having to go through this equivalence. So in fact, that's what we're working on now, and we have some results, but not really, still not, I would say, not completely satisfactory results about that. Okay, so that's the first thing. But in any case, we do get a categorical G action on these categories of modules for this Gelfand-Cetlin algebra. Okay, so another good thing about this is that, okay, so I mentioned quiver varieties, which are a special case of these Higgs branches earlier in the talk. And these quiver varieties are supposed to be related to these, they're Higgs branches, and these guys are the Coulomb branches of the same theory. And in that case, we say the two spaces are symplectic dual. And when we have these symplectic dual spaces, there was an expectation there would be some causal duality between categories of modules, specifically category O's between these two different spaces. And so category O is between our y lambda mu and the quantization of the covariety. So using this theorem here, this equivalence, and using some previous work due to Varignola, Vassereau, Rouquier, and Webster that relates these KLR algebras to quivarieties, we can establish this causal duality. And in fact, this point number 2 has been generalized by Ben Webster to any pair, well, maybe some hypothesis, but pretty much any pair of a Higgs branch and Coulomb branch defining this BFN way. Okay, so now lastly, say we're in the special case where we take y lambda mu to be this universal enveloping algebra SLN mod, the positive part of the center. Now, of course, enveloping algebra SLN has been studied for 100 years, so you might think that everything about it was known, but surprisingly, this category of Gelfand-Cetlin modules has been studied, but in fact, for example, the number of simple Gelfand-Cetlin modules in this block, like with this 0 central character, was not known. So this is actually an open problem posed by some guys back in 1991, and also has been worked on by Futorni and was discussed, like this basically the subject of his 2018 ICM address. So this problem is now solved using our theorem because, for example, the number of simple modules here will be just the same as the number of simple modules here because of this equivalence, and the number of simple modules here is well understood. For example, it's known what the Grothendieck group of the right-hand side is because it's known what it categorifies. So in this way, we actually solve this kind of classical problem by accident. Okay, I guess I'm a little early, but that's the end of my talk.
Let's thank Joe.
Yeah, thanks.
Questions, comments?
Dave?
For the first part of your theorem, I guess that the answer is maybe that you're still working on it, but if mu is dominant, it seemed like things were easier earlier on. Is this any easier, or is it just?
No, I think like it seemed like things were like somehow it seemed like things were easier when mu is dominant, but actually they're not really easier. These once you start thinking about things in this Coulomb branch viewpoint, then these algebras y lambda mu or these spaces w lambda mu are just as easy to work with or hard to work with when mu is dominant or mu is not dominant. So one interesting relation, since I have a minute or something, since I did finish early, let's say I can say one new thing. So one thing which we recently proved, in fact, it's now in the archive, is that which we sort of, okay, let me state the theorem, then I'll say more about it. So for any lambda mu, there's an action of the additive group on w lambda mu such that the affine Grassmannian slice mu plus alpha I, which is 2 dimensions smaller, is isomorphic to the Hamiltonian reduction of this w lambda mu by the action of GA. So and there's a quantized version of this theorem as well. So for example, when we're in this, say, dominant situation, like one maybe interesting special case of this is like this lambda equals n omega 1 situation, maybe mu any, like which is forced to be a partition of n, otherwise this space is empty. Sorry, any dominant. In this case, these spaces here are Slotaway slices, they turn out. And here we have a statement about Hamiltonian reduction between 2 Slotaway slices, which was basically known, can easily be deduced from work of Gann and Ginsburg. So there's a kind of generalization of this to any lambda and mu. And this is the example of something that yeah, if mu, if we sort of tried to do this for many years for all lambda mu, but since we didn't know what should happen when mu is not dominant, it was very confusing. But now that we knew what should happen when mu is, what the definition of W lambda mu is for non-dominant mu, it's actually not that hard to establish this kind of thing. Now this sounds super promising. It sounds like this is a great connection between W lambda mu and W lambda mu plus alpha I, which should allow you to define these functors that I wanted back here. But it turns out that the somehow that Hamiltonian reduction I just wrote down somehow doesn't quite work for defining functors because it doesn't play well with this Gelfand-Zetlin integrable system. On the other hand, there's like a more complicated kind of Hamiltonian reduction which really uses the Coulomb branch theory, and using that you can define these functors. So that's kind of work in progress. So this theorem is sort of like a first approximation of how you would define those kind of functors.
More questions? Okay, so thank Joel again.
You're welcome. Thank you. Nice to see you all.
Okay, so
Should we go for beers?